Welcome to The Explainer. Today, we are diving into what is honestly a genuine cosmic detective story. You know, if you think you know our galaxy, the Milky Way, like with its neat, luminous spirals that we're all so used to seeing, well, prepare to be a little surprised. We're exploring a fascinating new discovery that is fundamentally redrawing the boundaries of our stellar neighborhood. For decades, we've, understandably, comfortably focused on the glowing, structured disk where our sun lives. But the most exciting astrophysical breakthroughs right now, they aren't actually happening in that bright center. They're happening way out in the faint, distant fringes.
So, the central question driving us today is simply this. What exactly is hiding out there at the absolute edges of our galaxy? We typically picture the Milky Way as this highly orderly, rotating disk of stars, right? But out in the extreme periphery, these massive, totally chaotic disruptions are playing out in the dark. We're talking about cosmic destruction on an absolutely unimaginable scale. Events that leave behind these ghostly traces. And it's really only recently that we've developed the observational sensitivity and the computational tools to actually spot the evidence of these violent gravitational encounters.
Section 1. Hidden Star Streams.
Until a recent breakthrough study published in the Astrophysical Journal, a multitude of fine, elongated ribbons of stars just passing right through the outer Milky Way went entirely unnoticed. Just think about these remarkably thin structures stretching all the way across the galactic halo. These are what we call stellar streams. They're vast cosmic remnants trailing incredibly far beyond our sun. And what makes these structures so profound is just how fragile they are. Unlike a tightly bound cluster of stars, a stream is a structure that's actually in the process of being dismantled. These faint ribbons are essentially the torn threads of the galaxy's outer fabric. They stretch for thousands of light years across the sky, completely invisible to the naked eye, and basically hiding in plain sight from older generations of telescopes.
Section 2. Cosmic Fossils.
To understand the exact origins of these streams, we really have to look at globular clusters. As you likely know, these incredibly dense groupings of hundreds of thousands, sometimes millions, of ancient stars orbit the galactic center. And they act as the ultimate cosmic fossils. Because they are extremely old and notoriously poor in heavy elements, they preserve the exact conditions of early galactic formation from literally over 10 billion years ago. They are relics from an era before the Milky Way even formed its familiar spiral arms. But, here's the thing, they aren't just static relics. They are dynamic participants in this billion-year-long battle against the galaxy's gravitational pull.
Because as these clusters travel through the Milky Way's massive gravitational field over billions of years, they don't just, float peacefully. They are subjected to colossal, shearing, tidal forces. The gravitational pull on the side of the cluster closest to the galactic center is significantly stronger than the pull on the far side. So over time, this differential force literally stretches the cluster, slowly stripping the stars right away from its compact core. It's exactly, and I love how the researchers put this, it's exactly like grains of sand escaping a torn bag. The galaxy just relentlessly shreds these ancient fossils, pulling stars out into the leading and trailing orbits to create those long, drawn-out stellar streams we observe today.
The contrast between a compact, intact globular cluster and a disrupted stellar stream is absolutely stark. On one hand, you have a tightly bound gravitational fortress, right? And on the other, a ghost town stretched across the cosmos. But the real goldmine for astronomers is finding a stream that is still physically linked to its intact parent cluster. This direct linkage is incredibly rare and highly prized, because when we can map both the surviving core and the escaping tails, it allows us to precisely measure the titanic gravitational forces responsible for the tearing. It essentially gives us the initial state and the final state of a galactic disruption event, which lets us calculate the exact forces at play.
Section 3. The StarStream Revolution. Historically, finding these streams was a massive, massive challenge. Astronomers relied really heavily on visual or just basic kinematic searches, basically hunting for pristine, perfectly aligned trails of stars moving together. But galactic reality is highly chaotic. Visual searches inherently missed streams that were shorter, wider, or kinematically offset from their original orbits due to complex galactic interactions. Enter the StarStream algorithm. Developed by a team led by Yin-Tian Chen at the University of Michigan, this completely changes the game by utilizing a complex physical model. Instead of just looking for lines in the sky, StarStream computes the actual gravitational potential and the precise dynamic history of the stars. It models how a cluster should disrupt over time, tracking the true physics. And this allows it to identify these streams even when their visual signature is entirely disorganized or deeply obscured by background noise. So, what was the immediate result of this physically motivated tool?
87. Before StarStream, astronomers had managed to identify fewer than 20 of these specific structures, and that was over decades of searching. Jumping to 87 potential candidates in just one study is a massive, unprecedented leap. It completely validates the shift from visual searching to physical modeling. It proves just how much dynamic, invisible history was hiding right in front of us, literally just waiting for the right algorithm to decode it.
Section 4. Mapping the invisible.
Now let's connect the dots on why this actually matters beyond just finding cool new stellar structures. The rate at which a globular cluster loses its stars certainly depends on its own density and its specific orbit, but it predominantly depends on the overall mass of the galaxy. More specifically, it relies on the distribution of the invisible dark matter halo that makes up the vast majority of our galaxy's mass. Because dark matter doesn't interact with light, we can only observe its gravitational influence. So these shredded ribbons of stars act as massive, highly sensitive galactic scales. By measuring the exact shape, length, and velocity dispersion of these streams, we get the precise kinematic measurements needed to finally weigh and map the unseen dark matter halo of the Milky Way.
And honestly, this is just the beginning. The next phase of this astrophysical research is going to leverage an unprecedented wave of next-generation observatories. We are talking about the Vera C. Rubin Observatory, NASA's Nancy Grace Roman Space Telescope, and DESI, the Dark Energy Spectroscopic Instrument. Because StarStream is physically modeled, rather than relying on simple visual pattern recognition, researchers are super confident it will seamlessly adapt to the massive tsunami of high-precision kinematic data these missions are about to unleash. We are moving from studying dozens of streams to potentially analyzing hundreds or even thousands, mapping the dark matter halo with incredible, unprecedented resolution.
By studying these fragile ribbons of ancient stars, we are essentially hunting the ghosts of our galaxy's turbulent past. When we combine next-generation telescope data with algorithms like StarStream and finally map this invisible mass in its entirety, well, what will the hidden weight of the Milky Way reveal about the ultimate origins of our cosmos? Will it confirm our standard cosmological models, or will it force us to completely rethink the fundamental physics of dark matter? It's a dizzying perspective for sure, and one that guarantees our cosmic detective work is far from over. Thanks for joining me for this explainer. Keep that curiosity alive, and we'll see you next time.